Let's start by talking about what a hash is. So a hash is usually a super compression of a file. So we have a big honking file, we hash it, we get a much smaller number, and the number has a couple of characteristics. First, it is difficult to impersonate, meaning the hash has a low incidence of collision. The likelihood of two documents producing the same hash is not impossible, but very, very, very unlikely. Secondly, it's typically a fixed size for most hash algorithms. And third, if you change as much as one bit in the file, you get at least a 50% difference in the output of the hash. So let me go through this and just kind of explain some of this to you. I've got a file here called MD5 hash. Let me open it up. And all it has in there, it says, this is a test. That's all it says. Now I've got a website here that's going to generate the hash online. I just drag the file out here, and it produces, I'm going to use MD5, but SHA-1, SHA-256 are better hashes, but this MD5 is fine for our example. Here's the hash of the file whose content says this is a hash. I'm going to paste that up here so that we have a semi-permanent copy of it. I'm going to change the file in just a second. Now you may know this, probably know this, that in ASCII, changing, when you go from a lowercase letter to a capital letter, you're just changing one bit, a single bit. So I'm going to just go from a lowercase t into this to an uppercase T. And now I'm going to drop that file in here. And it's also going to produce a hash, but the hash is going to be significantly different. If you compare the two here, you'll see that it's in hex, but you see quite a bit of difference. And again, there's the general, what we're shooting for and what most hashes achieve is a single bit difference will give you at least a 50% output difference in the hash. Now that's our hash piece. Now we're going to come back to that in just a second, but before we get back to it, we want to talk about cryptography a bit. So let me start by giving you a quick definition of what cryptography does, and this will help, I think, you to see why we have to decrypt so much information. Cryptography takes meaningful data and makes it appear random to everyone except the intended recipient. Let me say that again. It takes meaningful data and makes it appear random to everyone except the intended recipient. The reason that's important, if you think about what we're doing with antivirus, IPS, URL filtering, application identification, we are looking for patterns. The very nature of cryptography eliminates those patterns. It isn't just that it keeps things secret. They look random, no patterns. Now, there's up until the mid-1970s, there was really only one way, at its essence, one way to do cryptography. We took some data, we took a shared key. That is the other end, the person who's receiving it, that I want them to be able to read it, and I have some secure communication channel, and we share a key that we're both going to use same key to encrypt and decrypt. During my lifetime, I spent 8 years in the Marine Corps, and one of the Marines' jobs was, if the embassy was overrun, was to take what we call a key schedule. This was a list of keys and dates and times. At this date and time, we're going to use this key, and then we're switching over this date and time to another key. It was our job to destroy that in case the embassy was overrun. The problem with that is it requires a pre-existing relationship between the sender and the receiver. So think about how we buy stuff online. You're going to Amazon for the first time. You don't want to have to wait a week for Amazon to send you a special key to use in your communication session. But that's all we could do up until the first publicly released what's called public key cryptographic algorithm, which has two keys. They're mathematically related, but there are two different keys. One key is used to encrypt the data. Now that key encrypts the data and you end up with the ciphertext, the encrypted data, but this key cannot decrypt. It can only encrypt. So if you now grabbed the ciphertext and you managed to capture the key, you still wouldn't be able to decrypt the data. To decrypt the data, you need a secret or private key, a separate key. This key decrypts the data. Now that ability to break out the functions where the one key encrypts it, but the same key can't decrypt it, a separate key is necessary to decrypt it, is going to make all the difference in the modern world for secure communication. So let me take you through a set of slides that I put together for this purpose. Bob is going to try to connect over. This is the essence of the SSL algorithm. I'm leaving a couple pieces out, but the pieces are not germane to understanding at the heart what's going on here. Bob is going to attempt to log into Amazon. Knock, knock, can I come in? Amazon says, let me verify my identity by sending you my certificate. Now, what's that look like? It has, who's the issuing certificate authority? Let's say it's GTE Cybertrust. The valid date ranges, the fully qualified domain name, the intended use, the public key, the serial number, the issuer's digital signature. Let's leave that one off for a second. All this information and more. This is just a summary. It's great to send that to Bob, but if an evil hacker got in the middle, he could change all that, right? So what we do to avoid that is we take all this information and we hash it. Now, you saw how long the hash was, and it was in hexadecimal. I'm going to make a pretend super simple hash. And my super simple hash is going to be this. That's the hash of all this. Now, you could put that into the field called signature, and you might think, well, that would help, and now I can, at the other end, I could run the same hash and check to see if it's changed. Except that if an evil hacker was in the middle here and changed all this, the hashing algorithm is public knowledge. So the evil hacker could then take and change that, rerun the hash, and put his own hash or her own hash in this field. So we're going to do something else. We're going to take this hash, and Amazon, not Amazon, the issuing certificate authority, GTE Cybertrust in my example, is going to take this hash and it's going to hash this, it's going to take the hash and it's going to encrypt the hash with their private key, resulting in something that looks like this. Whatever the change in the encryption resulted in. That's going to go here into the signature. Now the certificate is going to be delivered to Bob's computer. Now Bob's computer is going to take and hash this, end up with a number that looks like this. Now, attached to this will be the signature. And in Bob's certificate store is a certificate for GTE Cybertrust, which includes GTE Cybertrust public key. Remember that they encrypted this on this end with their private key. So now the public key will decrypt it. And when we go through that decryption process, if we end up with this, Bob knows two things for sure. Number one, GTE Cybertrust is really genuinely the one saying this is Amazon, meaning I'm likely to trust the content of this. And number two, the content has not been changed. All of this is the same, because if it wasn't the same, he wouldn't have gotten, his current hash of this would not have matched the decrypted hash. Now, that's the first step in our SSL process, but there's a little bit more that has to happen. You might think that because we now have Amazon's public key, all we have to do is encrypt the information, the session, with Amazon's public key. The problem is that public key cryptography, or asymmetric cryptography, takes between 1,000 and 10,000 times more computing power, more cycles per second, than does symmetric cryptography. So instead of doing that, we now instruct Bob's computer to generate a number. And let's say the algorithm we're going to use is AES 128. Bob's computer now has to generate a random 128-bit key. Now let me stop here. Generally speaking, computers have a very difficult time generating random numbers, so you often see this in the literature as pseudo-random. Although certain computers can generate random numbers. Certain of Fortinet firewalls can generate random numbers. You can look up in the literature and see which ones. They can generate genuinely random numbers. They often have to have an external source for that, but they can generate genuinely random numbers. But usually it's a pseudo-random number. For our purposes, I'm just going to say random. So we generate this random 128-bit key. AES stands for the Advanced Encryption Standard. It's a symmetric algorithm that's really strong and very light. And so what's going to happen is Bob will generate this 128-bit key. We will now take that key and we will encrypt it with Amazon's, that's Amazon's public key here. And we end up with this number, which is now encrypted. We then send that number down to Amazon. Amazon decrypts this number with their secret or private key. Now, both ends have a copy of this number right here, and both ends will use that to encrypt the session, which is why it's called the session key, and keep it secure from prying eyes. And that's there's some extra steps in SSL that are designed to make it seem more random, but in a nutshell, that's the SSL process. Does anybody have a question about that so far? Let me jump ahead then and go to the decryption process, which we'll cover in the slides in a few minutes. In this case, we're still going to use Bob and Amazon, but we're going to stick a Fortinet firewall in between and tell it to decrypt this session. So it looks like this. Once again, Bob says, knock, knock, can I come in? Amazon sends its certificate. But when the certificate, although the certificate's addressed to Bob here, when the certificate goes through the firewall is going to proxy that certificate. It's going to store it and generate one that looks kind of like it. Most of the information is the same between these, but a few things are changed. Like, for instance, the public key, instead of being Amazon, so here it's from, this is Amazon's public key, but here the public key is the firewall's public key. And here we had the certificate being signed by GTE Cybertrust, but now we're going to say this will be signed by, let's make the Bob part of our company, example.com. This will be assigned by example. That's good enough. By example.com. They're the issuing certificate authority. So now we've made those changes. We're going to get and rehash, once again, hash all this. And perhaps that result will be this. And we're going to take and encrypt that hash with example.com's private key. And maybe the end result of that would be this. Now that gets delivered then down to Bob's computer. Because, and the first thing Bob's computer is going to do is to take all of this and hash it and end up with a result that looks like this. Now, because this is part of our organization, Example Incorporated, Bob's computer has had added to its certificate store example.com as a trusted certificate authority. So the first thing we look and says, do we trust example.com? Yes, we do. We generated the hash. Now we take the hash that was already in the signature area and we decrypt it with example.com's public key. So we use the private key up here to encrypt. We use the public key to decrypt, and we're going to find that it matches. It matches down here. And so now Bob's computer now knows two things. Number one, this really is coming from Amazon. And number two, nothing in this certificate has been changed. The only problem is both of those things are lies. But because we trust the certificate authority, we believe the lie. Now, we're using this lie for good, never for evil, but it is nevertheless a lie. Now, Bob's computer does what we did before. We generate the AES key, and we encrypt it with what we think is Amazon's public key, but is really the firewall's public key. So we encrypt that, we get this result. We send that result up to Amazon, but what we do instead, it gets intercepted by the firewall. The firewall decrypts this with its own private key. So now it has a plain text copy of this key, but then it re-encrypts that with the real Amazon public key, delivers that to Amazon, Amazon decrypts it, and now three entities have a copy of the plain text key, Bob, the firewall,